At first, we saw this. We thought we understood how gas giants work. Then, more than 1,200 light-years away, we found something impossible to ignore. A giant that pushes planetary physics to its limits. It began as an anomaly. Every 6¼ days, the star dimmed, a pattern consistent with a large transiting planet. To confirm it, astronomers measured the star's wobble using radial velocity, but the signal was extraordinarily weak. After nearly 4 years of observations, the data revealed the full picture. The planet was enormous, about 1.5 times Jupiter's radius. A world that large is expected to be much denser than this. Its mass is only about 14% that of Jupiter. That gives it a density of just 0.059 grams per cubic centimeter, roughly comparable to cotton candy. And this is where the real mystery begins. Worlds this inflated are usually easiest to explain when they're young. Over billions of years, they cool, contract, and become denser. But this planet orbits in a system roughly the age of our sun. By standard evolution models, it should be significantly more compact by now. Something must be maintaining this planet, or perhaps reinflating it beyond what standard models predict. So, what is keeping it this puffed up? Tidal heating may play a role. If the planet's orbit is even slightly elliptical, the gravity of its star would constantly stretch and compress it, much like squeezing a stress ball. That flexing can generate internal friction, and friction produces heat. Over time, even a little tidal heating could slow its contraction. But there's a problem. For a planet this extremely inflated, tidal heating alone may not be enough. Another possibility lies in the planet's atmosphere. At high temperatures, part of the gas can become ionized and electrically conductive. Winds moving through the planet's magnetic field could generate currents that convert some of that energy into heat within the planet's interior. For now, no single explanation fully accounts for what we observe. But this is only where things start to get truly strange. For decades, planets around stars this hot were expected to be rare and difficult to survive, until we found this. It orbits so close to its star that a year lasts just 36 hours. On the planet's day side, temperatures soar to about 7,800 degrees Fahrenheit. That's 4,600 Kelvin, hotter than the surface of some stars. At these extremes, the familiar rules of chemistry begin to break down. The radiation from the star is so intense that hydrogen molecules cannot remain intact. They're ripped apart into individual atoms in a process known as thermal dissociation. A molecule is not rigid. Think of it more like two atoms connected by a tiny spring. Heat makes that spring vibrate faster and faster until it snaps. Supersonic wings sweep this atomic gas towards the night side. There, in the relatively cool of 2,500 Kelvin, something remarkable happens. The atoms find each other and recombine into molecules, releasing heat in the process. In effect, the entire atmosphere behaves like a giant chemical engine, tearing molecules apart on the day side and rebuilding them on the night side. Driven by relentless ultraviolet radiation, the upper atmosphere becomes so energized that hydrogen escapes into space. The planet may be losing millions of tons of matter every second, surrounding itself with an enormous envelope of escaping gas. It looks like a typical super-Earth. Its density is almost exactly the same as our own rocky home. But there's a massive catch. You see, TOI 1452b is heavy, about 5 times more massive than Earth. Usually, having that much stuff means gravity should have crushed its rocky insides into a much denser, tighter ball. And yet, it didn't. One of the best explanations is that a large fraction of this world may be made of water, perhaps as much as 30% by mass. For context, all the oceans on Earth make up less than 0.1% of our planet's mass. This isn't just a planet with an ocean, it's a giant cosmic water balloon. At sufficient depth, pressure could force that water into exotic high-pressure ice. It may reach temperatures of hundreds of degrees and still remain solid. In that form, it could create a barrier between the ocean and the rocky interior below. And then there's another twist. Scientists suspect the planet may be tidally locked, meaning the same side always faces its star. If so, one side would live in permanent daylight, while the other would never see the star at all. But the most intriguing part is that we still don't actually know what it looks like. The James Webb Space Telescope may soon study this world's atmosphere in detail. Scientists around the world are waiting for the spectral data to tell us what is really happening in that atmosphere. If this planet truly is water-rich, it could help redefine how we classify and how we search for Earth-sized worlds beyond our solar system. Imagine a planet that doesn't just look dark, it looks like a hole punched into the universe. Trace 2b is a hot Jupiter so close to its star that it should be glaringly obvious. Yet in visible light, it's almost invisible. Measurements from Kepler showed its reflectivity is under 1%, and the best fitting models put it as low as around 0.04%. In other words, it absorbs essentially everything that hits it. And here's the part that feels unreal. Kepler didn't discover this by seeing the planet shine. It detected it by pulling an absurdly tiny signal out of the noise, only about 6 parts per million change in the system's brightness across the planet's phases. That was, at the time, the faintest visible light phase signal ever measured for an exoplanet. But Trace 2b isn't perfectly black. It's so intensely heated by its star that its atmosphere should glow faintly red, like a coal at the edge of a dying fire. A planet that's black in reflected light, yet still smoldering from within. So, what's eating the light? Trace 2b is far too hot for bright, reflective clouds like Jupiter's. Instead, its atmosphere likely contains strong optical absorbers, elements like sodium and potassium with broad absorption features, and possibly additional high-altitude haze or soot-like particles that darken the planet even further. The problem is, our models still struggle to explain just how extreme that darkness really is. And then comes the final twist. Recent transit timing studies hint that its orbit may be slowly shrinking. If that signal is real, then Trace 2b is not just one of the darkest worlds we know, it also may be slowly spiraling towards its star. Forget Saturn. Meet J1407b. A world that truly deserves to be called the Lord of the Rings. When astronomers first examined the light curve of its parent star, they assumed something had gone wrong with their instruments. Normally, when a planet passes in front of its star, the result is simple: a smooth dip in brightness lasting a few hours. But this was nothing like that. For 56 days, the star faded and flickered. It looked as if something enormous, layered, uneven, and immensely wide was drifting across it. When researchers finally modeled the data, the explanation was astonishing. The unseen object is thought to be a massive companion, possibly a giant planet, possibly something closer to a brown dwarf. And surrounding it is a colossal ring system. Not a handful of rings like Saturn, 37 distinct rings. The scale is almost impossible for our brains to grasp. The entire structure stretches nearly 90 million kilometers, about 200 times wider than Saturn's rings. If this system replaced Saturn, its rings could stretch across a huge part of the sky, dozens of times wider than our full moon. That doesn't mean they would blaze brightly overhead, but in sheer apparent size, they would be enormous. But inside this vast disk lies an even deeper mystery. A wide, empty gap. In ring systems, gaps like this are rarely accidents. Gravity is a sculptor. A forming moon may be carving a path through the disk, sweeping up dust and ice as it slowly grows. In other words, we may be witnessing the birth of moons. Given enough time, some of that material may assemble into satellites, gradually transforming the disk into something more like a moon system. But for now, J1407b remains one of the most extraordinary ring systems ever inferred beyond our solar system. PSR J1719-1438b, a world that is less a planet and more a cosmic zombie. Its history is a story of stellar cannibalism. This object orbits a pulsar, the collapsed core of a dead star, spinning about 173 times every second. Pulsars are among the most extreme objects in the universe, and living next to one is anything but gentle. Long ago, this object was likely a white dwarf, the dense stellar remnant left behind when a sun-like star dies. But the pulsar was hungry. Over time, its immense gravity and radiation stripped away the star's outer layers, peeling it apart piece by piece, until only the exposed core remained. What survives today is something deeply strange. In mass, it's roughly comparable to Jupiter, but it's compressed into a body only about the size of a large planet, making it more than 20 times denser than Jupiter. In a very real sense, this object isn't a normal planet at all. It's the remnant core of a dead star. And inside that core, the dominant element is carbon. Under crushing pressure, carbon atoms lock into a rigid crystalline lattice. On Earth, we know that structure by a familiar name: diamond. On a planetary scale, the result is extraordinary. A dense body, rich in crystalline carbon, drifting through space. And if you tried to price a world like this in human terms, the number would be so absurd it would stop meaning anything at all. What we've just seen is not just 6 strange planets. There are 6 places where the universe has pushed our ideas to the edge. Each one reveals a different weakness in our models: structure, heat, composition, darkness, inference, even the meaning of the word planet itself. These worlds are clues, because the universe teaches us the most when reality refuses to fit our models. And every time that happens, our theories improve, our searches grow sharper, and we become better at recognizing worlds stranger than the ones we already know. These planets are not the end of the story. They're where the next one begins.